A Cisco router's primary job is routing packets across networks, but in high-volume networks, routers can become seriously congested with packets. To understand why, we'll take an in-depth look at router queues, how they work, and the unpromising journey a packet takes each time one enters a router's ingress interface. Here, a packet just arrived on an ingress interface, but what will the router do with it? Before discussing this, we need to understand the preparations a router goes through on initialization to prepare for the arrival of packets. When the Internetwork Operating System, better known as iOS, is initialized on a router, one of the first things it does is allocates and assign a portion of the router's dynamic random access memory, or DRAM, for packet storage. Typical of operating systems, it has a scheduler, memory manager, and CPU resource manager, among other features. In fact, a router's DRAM memory is split into two sections, local storage and I/O mem, or I/O memory. Local storage is where routing tables, the running configs, and I/O data is stored. I/O memory is where public and private pool buffers and receive and transmit rings are located. When you execute the show version command and scroll to the router's memory capacity, you'll see two numbers separated by a slash. The first number represents the router's local storage memory and is where routing tables, running configurations, and iOS data are stored. The second number represents the I/O memory portion of DRAM memory and is where the router stores packets. I/O mem is also split into two types of storage. The first is public storage and the second is private storage. When iOS is first initialized, it creates private storage pools in I/O mem and assigns each interface its own private pool. Private pools are also called receive queues. iOS also assigns each interface an input and output queue from public pool buffers. Public pools also contain general buffers that iOS uses to store packets it generates. Input queues act as overflow buffers for receive interfaces, and output queues act as overflow buffers for transmit rings. Finally, what are receive and transmit rings? These rings are special software constructs that iOS creates at initialization and reside in the I/O memory buffer space. This software construct is called a ring because it processes packets in a circular manner or in a first in, first out process. Rings are called hardware queues for two reasons. One, they belong to egress and ingress interfaces. Two, they store information about where incoming packets can be stored in memory when polled by an ingress interface, or where packets that have been processed and are waiting to be transmitted can be found in memory by an egress interface. Controllers have direct memory access and can store or retrieve packets themselves from memory. Ring buffers hold the information they need to do so. Let's look under the hood of G00's receive ring. The ring has 10 buffers labeled 0 through 9. To the right of the ring is its descriptor, better known as a ring descriptor. The descriptor references the buffer addresses at which a packet can be stored and who owns the buffer. The receive ring reads its descriptor to learn the memory locations new packets can be stored as they arrive to the interface. The green right head points to an empty buffer or queue on the ring that packet buffer addresses can be written to on the ring as they are learned. And when the G00 interface polls its ring to learn the address to store an incoming packet, the blue read head reads the next address on the ring queue and provides that information to the controller. In this example, the green right head is reading the ring descriptor and populating G00's receive ring. And as new packets arrive to the G00 interface, the blue read head reads the next ring queue and sends that information to the controller. The controller then uses direct memory access to store the packet in the appropriate packet buffer based on the information that was sent to it. Next, let's look at the transmit ring. Like the receive ring, it too has 10 buffers and its own ring descriptor. After new packets have been processed by the CPU, iOS writes their location to the outgoing interface's ring descriptor, which in this case belongs to S00. The ring reads its descriptor and writes each address to a ring queue in the same manner the receive ring does. In this example, S00's transmit ring is being populated with the addresses of packet buffers storing packets that have been processed by the CPU and are waiting to be transmitted. Once packet buffer addresses are placed on the ring, iOS releases the initial receive interrupt it received when the packet was assigned to the packet buffer initially. At this point, iOS has done its part and now waits for the controller to do its part. The packet will remain in the same packet buffer, however, until the controller has polled its ring, learned the address of the packet buffer the packet resides, and serialized the packet. Once this happens, the controller sends a transmit interrupt to let iOS know that the packet has been transmitted and that the buffer is free to be used to store new incoming packets. However, once ring queues are full, packets waiting to be transmitted will be moved from their original packet buffers and placed in S00's default output queue. This default output queue is an overflow buffer for packets whose original packet buffer addresses don't make it onto S00's transmit ring. When this happens, the original receive interrupt iOS received when these packets were first assigned to the buffer is released. However, the packet must still be assigned to the transmit ring before it can be processed by the ring. In this example, S00's transmit ring is full and waiting to feed the S00 controller packet buffer addresses when it polls for them. As the S00 controller polls for the next address, the blue read head goes into motion. The blue read head reads the next packet buffer address and sends the information to the controller. Now that the controller has the address of the next packet buffer to be processed using direct memory access, it retrieves the packet from the packet buffer. Once the controller serializes the packet, it sends a transmit interrupt to iOS, which lets iOS know that the buffer is empty and can once again be used to store incoming packets. iOS then reassigns the buffer back to the original owner. The original owner will be the ingress interface that the now transmitted packet was initially received on, or iOS, if iOS temporarily loaned that interface one of its public buffers. As queues on the ring become available, packets waiting in S00's default output queue will be processed next, ahead of newer packets waiting to be transmitted, even if they can immediately be transmitted by the transmit ring. Therefore, the default output queue's packet buffer addresses are written to the ring next. At the end of this example, we see how the addresses of S00's default output queue is written to its ring and are then processed by the S00 controller. Now let's observe the process that takes place from the time a packet enters a router's ingress interface until it is serialized by its outgoing interface. In this example, a packet arrives at G00's ingress interface. Next, the interface polls for the next available receive ring. In this scenario, G00's receive ring number 2 turns on, indicating that it will be used to service the incoming packet. It gives its descriptor to the interface controller, letting the controller know its identity and where to store the packet. At this point, G00's receive ring number 2 has directed the G00 controller to store the packet in G00's private pool receive queue labeled GP002. Using direct memory access, the G00 controller places the packet in the GP002 packet buffer. Next, the G00 controller sends an interrupt to the CPU letting it know that a packet needs to be processed and where it can be found. Then the CPU begins processing the packet. iOS uses self, fast switching, or process switching to determine the forwarding information the CPU needs to write to the packet's header. Next, iOS does a route lookup using self to find layer 2 forwarding and next hop information. Finally, when the CPU finishes its rewrite, the packet is placed back into G00's GP002 receive queue and waits to be transmitted. In this scenario, the G00 receive buffers are full, yet another packet just arrived and needs to be stored. In this situation, the receive input queue is used and the packet is placed in G00's default input queue labeled GI003. But if all the receive and input buffers were full, the packet would be dropped unless an iOS public buffer was available, as one is here. It's common for iOS to loan buffers to an ingress interface when its private buffer pool is exhausted. However, if no public buffers were available, the packet would be dropped as is demonstrated here. This is called tail drop. Now let's look at what would happen if all of S00's transmit rings were full. In this scenario, a packet is waiting in G00's receive buffer to be transmitted out of S00. iOS checks for an available transmit ring, but they're all busy transmitting other packets. Therefore, iOS stores packets in S00 default output queue until one of the interface's transmit ring becomes available. When this happens, iOS releases the initial receive interrupt. Finally, transmit ring 1 is available and iOS begins processing packets from the default output queue in the order that they were placed into the output queue. Once the packets here is transmitted, it sends a transmit interrupt to iOS informing it that the packet has been transmitted and the ring is clear to transmit another packet. iOS clears the transmit interrupt and assigns another packet to the ring if one is ready. By default, transmit rings are first in, first out, and the default output queue is also first in, first out. In summary, receive and transmit rings are also called hardware queues because they are owned by hardware controllers. Both process packets in a circular manner. Both uses a first in, first out queuing method to process packets. They also have a ring descriptor. If rings didn't have a ring descriptor, they'd have to do an exhaustive search throughout memory to find the next packet buffer available to store packets or to find the next one holding packets that are ready to be transmitted. iOS writes the next location to store or retrieve packets to the descriptor. This capability severely reduces the amount of time a packet spends inside a router, thereby reducing packet latency and delay. Like rings, an egress interface's default output queue also uses a first in, first out or FIFO queuing strategy. This is the fairest queuing strategy packets can get. But what happens when delay-sensitive packets like VoIP gets processed using FIFO queuing? Will this default queuing strategy be right for these packets? We'll look at this in the next presentation called Software Queuing.